In this video, we look at a couple more examples of surface integrals of vector fields. So in that case, what we're looking at are flux integrals. And here is the notation, a double integral over a surface, f dotted with dA. And here is the more working notation of that flux integral. And we can see here that there are a series of steps to go through. The first thing you need to do is to find a parametric form of the surface. That is step number one. Okay. You then need to find n, which is the outward pointing normal. So you need to make sure you compute the cross product in the correct order so that when you have your surface, that the cross product you get is a vector that points outward, right? So you want the outward pointing normal. That is the positive direction. And if you have vectors that are pointing in the opposite direction of the vector n, then that would be a negative flux. You would have more vectors crossing into the surface rather than pointing outward. So that's what you need. Make sure you have an outward pointing normal. Make sure you compute the cross product correctly. And then in step 3, you need to compute the vector field along the surface. Then you need to compute the dot product. And then you will have, once you compute that dot product, you're going to have a double integral on your hands that you might need to figure out how to evaluate. You may need to reverse the order of integration. You may need to change coordinates by switching to polar coordinates, for example. So using all the different techniques we had in the integration section. Okay. So here is a quick example. All right, just to kind of get us going on this problem. Here we have, let's say in part 3, we have a vector field. In this case, it's a really simple vector field. It is the vector field 0, 0, 3, right? And we want to compute the vector surface integral of this vector field over the surface, which is just the plane z is equal to 2. And that plane is drawn over top of a rectangle -2 to 2, -1 to 1. So what we're seeing here in this example is the surface given by the plane. It's in the z is equal to 2 plane. So there's our surface, z is equal to 2. But our surface is actually a restricted region of that plane. It's actually the plane that only goes from -2 to 2 in the x-axis, and then only goes from -1 to 1 on the y-axis. So what we're actually looking at here is only part of this rectangle, only part of the plane. So we would like to figure out what is the flux of this vector field, and the vector field is equal to 0, 0, 3, so this vector field is always pointing in the z direction. Okay, so here is your vector field. The blue part is your surface here, and if we compute a flux integral f dotted with dA, okay, through the part of the surface, we would need the vector field along the surface, okay, and our surface is otherwise known as, let's do the parametric form of it, it's u for x, v for y. We'll do the Monge parameterization, and z is equal to 3. I'm sorry, z is equal to 2. We had the plane z is equal to 2. And therefore we know that the normal vector is negative partial with respect to u, negative partial with respect to v, and then 1 for the z entry. So there is our normal vector for the surface, the outward pointing normal. We can see here that the 1 is a positive number, and so the normal is pointing upward. Okay. All right, and so what we're looking to do here now is find the vector field along the surface. And since the vector field is 0, 0, 3, there's no u's and v's to plug in our different x, y, and z values. So the vector field along the surface is 0, 0, 3. And then we're going to dot product that with the normal vector, negative 1, negative 1, 1. And then we're going to integrate over du dv, where u is the x goes from negative 2 to 2, and v is the y variable, goes from negative 1 to 1. And if you compute this double integral, we will be integrating 3, and because 3 is a constant, it will come out in front of the integral, and then we will integrate over du dv, which gives us 4 multiplied by 2. So here we will be getting 3 times 8, where 8 is the area of this region. So in blue we had the area was equal to 8. So that's something like meters squared. And the vector field, which was 0, 0, 3, was maybe something like liter per meter squared. So 3 times 3 liters squared per minute times 8 meters squared comes out to be a value of 24 liters. So that's why these integrals are called flux integrals. The vector field has physical units like a flow rate, and the surface integral, when you do the surface integral, you're adding up the flow rate across a certain area, and the end result is a total amount of flow, 24 liters through the surface. Okay. So what's a more interesting question perhaps is, what if the vector field, like we can see here on the right, we can see that our plane is not necessarily, our plane is kind of on an angle, right? We can see this plane here, and then we can see a little portion of this plane in red, right? So we don't want the flow through the whole plane, but only this little corner portion of the plane. And the vector field is in blue there. We may have the vector field kind of not always pointing in the same direction. So how much of the vector field there in blue is actually flowing through the little red region? Okay, and that's what we'd like to look at in this next example to illustrate the flow rate. Okay, so let's add a page below, and let's try to do this problem now. Okay, and the question is essentially to find the flux of a given vector field, and let's say that that vector field is equal to yxz. That was the blue vector field that I showed you in the previous picture. And then let's say that we have a plane. Our surface is given by a plane, and we know that a plane is of the form some number times x plus some number times y plus some number times z equal to some constant k. And so here we have a plane that is 2x plus 3y plus 4z equal to 20. So here we have a plane, and we want that plane to only be the part of the plane where x goes from 0 to 2, and we want y to only go from 0 to 1. So this information about the surface will have to be given to you, and you will also have to be given the vector field. All right, that is the necessary information you need to do a flux integral. You need a vector field, and you also need a surface description. Okay. Now, if we're going to finish this integral, we need to do a double integral over u and v. So we need to come up with a parametric form of the surface. We need to evaluate the vector field along the surface, and then we need to do a cross product, find the direction RU cross RV of the surface, and then integrate du dv. Okay, so one of the obvious ways to find the equation of the parametric form of the surface is to do the Monge parametrization. and that will tell us that r of uv, we're going to let x is equal to u, y is equal to v, and then we're going to solve for z as a function of x and y. So z is equal to 20 minus 2x minus 3y divided by 4. So z is equal to negative 1/2 x minus 3/4 y plus 5. So that makes the surface parameterization negative 1/2 u minus 3/4 v plus 5. There's our surface parameterization. And we know that our normal vector for a Monge parameterized surface is RU cross RV, and that will ensure that we get the partial derivative of this z entry with respect to u, but we have to put a minus partial with respect to u, minus partial with respect to v, 1. The partial derivative of this with respect to u is positive negative 1/2, but when you take a negative, negative makes a positive. You will get 3/4 here, and then 1 for the z entry. Okay, so that handles our normal vector that we're going to use. Let's look at the vector field along the surface, r of u comma v, and our vector field was y, x, z, so y was equal to v, x was equal to u, and z is equal to minus 1/2 u minus 3/4 v plus 5. Okay, so now if we compute the dot product, right, the vector field dot producted with n, okay, let's see, the vector field dot producted with n, sorry, I'm just double checking something here. There was our vector field VU, that, and then I need to dot product it with, with this vector here. So that would give me 1/2 of V plus 3/4 of U, and then 1 multiplied by this is minus 1/2 U minus 3/4 V plus 5. So here we can see that we have a 3/4 U and a minus 3/4 U. Oh, that's a V. Sorry, problem with using V's. So let me see, here are my U's. 3/4 U and minus 1/2 U. 2/4, so it makes 1/4 U. And then the V's, what is that? 2/4 V minus 3/4 V, so minus 1/4 V, okay, plus 5. So that is what we need to integrate. We need to do a double integral of that dot product, 1/4 of U minus 1/4 of V plus 5. We need to integrate with respect to U and V, and because U and V are given, we knew what part of the plane, and U is equal to X, so U will go from 0 to 2, and V will go from 0 to 1. And if you evaluate that integral, you will get 41 divided by 4. Okay? Now what we just computed, was this problem right here, right? So we had the parametric form of the surface, R of uv, and then we found RU cross RV du dv, so we had a little part of the surface, okay, and we had n RU cross RV, we had our normal vector pointing this way. And because the vector field is this blue thing, right, every time the vector field on this part of the surface was pointing in the same direction as the normal vector. So the surface and the vector field were all pointing in the same direction. And so there was a net positive flow through this surface of 41 over 4. So that would be 41 over 4 liters of flow if we had a flow rate of this in liter per meter squared. du dv came out in meters squared. So we had 41 over 4 liters of total flow through that part of the surface.